everybody, welcome to Science Explained channel, and we are going to talk about the quantum numbers. In the introduction section, we will talk about the definition, the types of quantum numbers, and Schrodinger's quantum numbers. And what are the quantum numbers? They are a set of discrete numbers from the quantum mechanics. They are not a set of continuum numbers as usual in classical physics. There are four quantum numbers: the principal quantum number n, the secondary quantum number L, the magnetic quantum number m, and the spin quantum number s. Three of them are obtained from the Schrodinger equation, n, L, m, and they are needed to describe the atomic orbital. The fourth quantum number, s, was obtained experimentally and theoretically by Dirac equation, by incorporating the relativity effect. Please watch our video about the atomic theory and atomic orbitals for more details about the Schrodinger equation. There are four types of quantum numbers, as mentioned before. The principal quantum number n, whose set of discrete numbers is 1, 2, 3, 4, etc., and represents the shells of the atoms, like it was also known in the Bohr's theory, the old quantum theory. The shells are K, N is 1, L, N is 2, M, N is 3, N is 4, and so on. The secondary quantum number L, or the orbital quantum number, or the angular quantum number, or yet azimuthal quantum number, divides the shells into smaller groups called subshells, or the types of atomic orbitals. The secondary quantum number L describes each type of subshell. The set of L is a set of discrete numbers beginning with 0, 1, 2, 3, until n minus 1. Each subshell, named as S, P, D, F, has a distinguished shape. For example, the S subshell is a sphere-shaped orbital, and the P subshell is a dumbbell-shaped orbital. The magnetic quantum number m, or the quantum number of the z component of the angular momentum, Lz, specifies each projection or orientation in each subshell. The set of Lz is a set of discrete numbers from minus L to plus L. For example, for L equals 0, M is 0. Then there is only one orientation. For L equals 1, M is minus 1, 0, and plus 1. Then there are three orientations in the space. It is called magnetic because it needs an external quantum field to give the different energies for each projection in each subshell. This was obtained by the Zeeman experiment, and it's called Zeeman effect. As we can see here, the L1 subshell and L2 subshell, when there is no magnetic field applied to the atom, and when it's applied a magnetic field B, we see that the three orientations of the L1 subshell is divided into three types, into three energies, three different energies. For the L equals 2, when it's applied the magnetic field, it is split into 5 orientations of this subshell. And the fourth quantum number, the spin quantum number S, has two projections, S plus a half and S minus a half, and it distinguishes the two electrons in atomic orbital. So let's talk about the Schrodinger's quantum numbers. As stated before, the quantum numbers L and Lm are consequences of the Schrodinger equation applying to the hydrogen atom. The Schrodinger equation is an eigenvalue equation. For example, the general equation is A times U equals lambda times U. When you apply a mathematical operator A, for example, the multiplication operator on a vector U, it gives a scalar value lambda associated to this vector. In the Schrodinger equation, the vector is the wave function psi, and the operator is the Hamiltonian H, which is the potential and kinetic energy operators, and the scalar is the energy E. The famous time-independent Schrodinger equation is this. The Hamiltonian H applied to psi gives E and the psi. The curious thing about the Schrodinger equation is that we have two unknown variables, psi and E, in one single equation. The Hamiltonian depends on the study case, which is the hydrogen atom in our case. In the Schrodinger equation, we have to begin with a classical starting model in order to obtain the Hamiltonian. As a consequence, we obtain psi and E simultaneously. The starting model for the hydrogen atom is a sphere like this, with a central potential in the core of the sphere, which is the proton, and one electron which has free movement, one translation movement and two rotational movements, where the variables are R for the translational movement, angles theta and phi. So, and the Schrodinger equation can be separated into the functions of the free variables of the electron of the hydrogen atom, which is given here. Psi is a function of free variables, which can be separated into the functions of each variable. R, capital letter, theta, in capital letter, and phi in capital letter. Then we go to one particle translational movement, which is one of the movements of the electron of the hydrogen atom. Then we go to the simplest case, that is one particle in the box. The translational movement is the motion in one of the three Cartesian coordinates, x, y, or z, and it can be one-dimensional, two-dimensional, where we have x and y, z simultaneously, and three-dimensional, where we have x, y, and z simultaneously. Here we have the example of one-dimensional translational movement and two-dimensional translational movement. The particle in a box is the simplest situation to describe the starting model for the translational movement, where the potential energy is zero. Be attention that is not the case for the hydrogen atom, but the results of the quantum number, the principal quantum number n, it is partially the same. Then the Schrodinger equation for one particle moving freely in the x direction is given here. When we say moving freely, it means that the potential energy is zero, the length of the box. Then, in this case, is a one-dimensional box. Then we have the Schrodinger equation for one particle moving freely, which means moving with potential energy zero in the x direction, which means it's a translational movement in one dimension. Then we have the Schrodinger equation with the kinetic energy operator the quantum kinetic energy operator and the potential energy operator, which is 0 in the limit of the box. The boundary conditions for this case, where L is the length, is x is 0, the lower limit, and x is L, the upper limit. The wave function psi is a function of x, which is 0 when x is 0, and 0 when x is L. The potential energy is infinite for x less than or equal to 0, or when x is greater than or equal to L. The potential energy is 0 when x is between L and 0. Then, with the help of mathematicians that found the solutions for several types of different equations, we obtain the solutions psi and E. The wave function for the one particle in one dimension is given here, where we have the quantum number n. In order to satisfy the boundary conditions that are given here for this wave function, n must be 0, plus minus 1, plus minus 2, plus minus 3, and etc. This is one quantum number. The unique difference that we have to pay attention is that the quantum number for the hydrogen begins with 1. It's only positive integers, okay? For the hydrogen atom, the principal quantum number is only positive integers beginning with 1. Here, for the one-dimensional translational movement of one particle, we have n that can be 0 and that can be negative integers. Then we go to one particle rotational movement. So let us analyze the rotational movement in a single plane, which is the ring, as we can see here, where the potential energy is 0, V is 0, with a constant radius r. In this case, there is only the kinetic energy operator T. The kinetic energy operator can be described in Cartesian coordinate or polar coordinate, but it's wiser to use the polar coordinate in this case. We see here the phi, which is the angle variable. Then, since r is constant, the partial derivative of the function phi over a constant r doesn't exist. The same occurs for the second derivative. Then we have a simplified kinetic energy operator. The boundary conditions for this particular case, where phi is the angle variable, is given here. When we have psi, where the angle is phi, it is the same for psi, where phi plus 2 pi occurs. Then we have a cycle, a complete cycle. In this case, the wave function is the same. Then the Schrodinger equation becomes the kinetic operator, where the unique variable is the angle phi. Then we have this derivation of the Schrodinger equation given here, and we are not interested in all the details of this derivation, but it's important to see that this part is replaced. These scalar numbers are replaced by this m squared, and we have this Schrodinger equation at the end. The solution for this Schrodinger equation is given here, where n is the normalization constant, which is necessary to obey a quantum postulate of the probability of finding the electron within the range from 0 to infinite, or minus infinite to positive infinite. Then by applying the boundary conditions, we have that this equation is, this part of the equation is 1. This is only true when m is 0, plus minus 1, plus minus 2, plus minus 3, etc. Which is the word quantum number, the magnetic quantum number of the hydrogen atom. Then we go to one particle spherical movement. The wave function for the one particle spherical movement is a particle moving in a surface of a sphere of radius a, which is a constant, and the potential energy is also 0 in this case, and the wave function is epsilon, or also called as spherical harmonics, and it is a product of the polar angle equation in horizontal plane, the theta, and the azimuthal equation in a vertical plane, phi, given here. The product of the theta and phi, the boundary conditions, and the corresponding Schrodinger equation, where lambda is given here. Then we have this equation, the Schrodinger equation for the one particle spherical movement. After some derivation, we have this equation, where the second part of the equation is the particle in a ring equation. It's similar to the particle in a ring equation. Then, as we saw in the particle in a ring equation, this equation is the m squared. Then, the first part of the equation is also the m squared. And this is an associated Legendre equation which has a well-known solution. And as result, we have the quantum numbers lambda and m. Lambda is L times L plus 1, and L is 0, 1, 2, 3, etc. And m is 0, plus minus 1, plus minus 2, until plus minus L. And the m and L are the quantum numbers. The same quantum numbers for the hydrogen atom. In this case, is the same. They are the same quantum numbers. The final equation is given here, where is missing the values for normalization constant for the theta and the normalization constant for the phi. But we see here is the solution for the associated Legendre equation of the first part of this equation. Okay? And the solution of the associated Legendre equation is given here, where m is a positive, we have this solution, and when m is a negative, we have this solution. As a consequence of the product of the theta and phi equations, we have the spherical harmonics, or, as we know, the atomic orbitals. Then when L is 0, we have the s orbital. When L is 1, we have the p orbital with free orientations. When L is 2, we have the d orbital with 5 orientations. When L is free, we have the f orbital with 7 orientations. Then we go to the 4th degree of freedom, the spin. The spin was not obtained in the Schrodinger equation. It was artificially incorporated in the wave function in order to obey the antisymmetry of the wave function. See the video about the electron configuration in the end of this video. In 1922, 4 years before the Schrodinger equation, the experiment of Stern-Gerlach revealed that the electron has a magnetic property from the silver gas. The silver gas, which has a 1 ampere electron, passing through collimator slits and the magnet, the 2 poles of the magnet, and this beam is deviated. It has 2 deviations, which is detected in this plate. Then is the first evidence of the anomalous Zeeman effect. In 1925, Phipps and Taylor performed the same experiment using hydrogen beam, which also has a 1 ampere electron, and obtained a similar result. One year before Schrodinger equation, which was then 1925, Uhlenbeck and Goldsmith proposed a formula for the spin magnetic moment mu as a function of the total spin angular momentum S and the magnetic dipole moment mu B. The total spin angular momentum S of an electron is given by this equation, where S is the spin quantum number, which is 1/2. The projection of the S of an electron is given by this equation. It has 2 projections, which are the 2 deviations of the silver gas beam, and then this represents the 2 projections of the spin. And here we see the pictorial representation of the magnetic dipole moment, where the magnetic dipole moment is mu as a function of the moment of inertia and the area. A similar result is applied to the magnetic dipole moment of the spin. Then the electron behaves as a tiny magnetic bar or a tiny gyroscope, with 2 possible orientations of its magnetic dipole moment. Finally, we come to the final considerations. Then we conclude that the electron has 4 degrees of freedom or 4 types of different movements: translational movement, 2 rotational movements associated with the polar and azimuthal angles, and the movement of the tiny quantum gyroscope. The degrees of freedom of an electron obey the corresponding set of discrete numbers called quantum numbers. Please visit the site of our book. The link is in the description of this video, which is the Introductory Organic Chemistry and Hydrocarbons, a Physical Chemistry Approach. Stay tuned to our next book, Quantum Mechanics and Quantum Chemistry, Detailed Historical, Mathematical and Computational Approaches. Please check our next video called The Atom Electron Configuration. The link is in the description and in the end of this video. Please subscribe to our channel, and thank you very much for your attention.